Hello, everyone. Thank you so much for joining us. We'll begin in a few short minutes. I'll just start with a couple of ground rules and event rules. So we'll be operating within the Microsoft Code of Conduct. We're really excited that you've decided to join us for today's session. I will be recording this session and we will post it on the Reactor website and on our YouTube channel if you wanted to watch it at a later date. Joining us today very graciously is Jaya Matthew. She's a senior data scientist at Microsoft, part of the Azure Global AI team. Her work focuses on the deployment of AI and ML solutions to solve real business problems for customers in many different domains. And before Microsoft, she used to work with Nokia, HP on many different analytics and machine learning use cases. She also has an undergraduate and graduate degree from the University of Texas at Austin in maths and statistics. So thank you so much for joining us. I will let Jaya take it away from here. Hi, Jaya. I think your microphone's muted.
Yep.
Perfect.
Can you hear me now? Yeah.
Yes, we can.
Okay. Yeah. Thank you, Eamon, and welcome to the talk. Thank you for dialing in, taking the time to listen to us today. So let's actually kind of minimize this. Yep. Okay, so let's first get started with a brief agenda of what we'll cover in the talk today. So most of us have actually heard of natural language processing in various domains. So we'll first get started with defining what is natural language processing, and that's essentially NLP for short. Then we'll get into some of the common application use cases that most of us have come across when we use our laptops, computers, phones. Then the second section would be where I introduce the concept of machine translation, MT for short. Then we'll actually get into some of the different waves in the evolution of machine translation and how it's actually reached the point it is today. Then again, we'll step back and look at some of the machine translation applications. Most of us have seen it in our day-to-day lives when we're trying to understand something in a foreign language. Then the third section and the fourth one is slightly more technical, where I introduce something called language models. So it's kind of helpful to understand a little bit about how these models are structured. So you don't have to understand the whole section, but just a slight gist of it would help you in the long run. Then we'll get into what is neural machine translation. That is what we use in most of our applications these days. And I'll wrap up the talk with a sample use case where I use speech translator and how you can customize that in the event that you're using it for any of your customers. Throughout the deck, I've actually embedded some useful links of blogs, papers, and stuff like that. In case you're actually interested in following up and reading more about the topic, I would appreciate if you actually hold off on the questions to the end of the talk. Ayman will actually monitor the chat for questions and we'll pull up all the questions towards the end. I think the entire talk should just take about 40-45 minutes, so we should have about 10 to 15 minutes at the end for Q&A. Okay, so let's get started. So the first section is what is NLP? Now, I think this is one of these buzz acronyms that we all have come across. So NLP is essentially natural language processing. It is a branch of artificial intelligence that deals with the interaction between computers and humans using natural language, just like how humans talk to each other. So we are hoping that we can communicate with a computer or any device, just like how we talk to another human. So it's much easier than having to code or program or anything. So the ultimate objective of NLP is essentially to read, decipher, understand, and make sense of human language in a manner that's valuable for the human and enables the computer to do something that helps us. Most NLP techniques rely on some sort of machine learning to derive meaning from what we are trying to say using our human language. So, like I said throughout, I've actually put in links, and I think it'll be interesting if anyone wants to know more about this. Okay, so now that we know what is NLP or natural language processing, I think most of us have seen some of these applications in our day-to-day life. So let's actually just quickly go through some of these and, it'll immediately strike you as, oh yeah, I've used this before. So word processors. So we've all used Microsoft Word, Grammarly, they all use NLP to check grammatical accuracy of text and SMSs. So many times when we type on WhatsApp, iMessage, or any of these things, it autocorrects. Sometimes it's annoying, but sometimes it does help you. So that does employ NLP in the back end. Then language translation. So many a times, I'm trying to understand a new language or a new banner somewhere. I might, use Bing or Google Translate. That's also an application of NLP. IVR, interactive voice response applications in call centers. So many a times when we call any of these call centers, very rarely do we directly go and talk to a human being. So there is an IVR system in place which kind of asks you to say something in a few words, is trying to understand what you're saying in that language and route you to the right agent. Then some of us do have personal assistant applications like OK Google, Siri, Cortana, Alexa in our homes. So we essentially speak in natural language to these devices and have them do something. So these are some of the top applications. Obviously, there are many more and the list is not comprehensive. Okay, so now that we know what is NLP, what it's used for, some of the applications, let's get into the next section, which is what is machine translation. So again, we have seen this in our day-to-day lives many a times. We go into, Bing Translator or Google Translate. And maybe I'm just proficient in English and I'd like to know how to say hello in, let's say, Hindi or maybe in French. So here I just type hello, and then in Hindi, it actually gives you in the native Devanagari script, and maybe I'm new to that language, so I actually don't know how to read that script. So beneath the actual script, you kind of see the transliterated version, which is, in this case, is Namaskar in Hindi. And now all these translators are so good that they even have the audio option where you can actually listen to how it's said in the native language. Now, maybe in French, this is a case where I write hello. Now the script in French is, I know how to read it because it's pretty much like English, so I know it's bonjour. Maybe I don't know how to say it the right way in the right accent, so the option to actually listen to it is there. So these are some applications of machine translation. It is essentially the task of automatically converting source text in one language to text in another language. So in this case, the source text was all in English because I was proficient in English. I'm interested in learning a bit of Hindi and French, hence that's what I was trying to translate to. So I think most of us have seen translator applications in our day-to-day lives. So this was an interesting application, how they very cleverly embed machine translation into our day-to-day lives. So this was an email I got a couple of months back, and the email was in French, and I do know how to read a bit of French, but not the whole thing. So they had a little button that I've highlighted in red in there where they kind of say, would you like to translate emails that come in French into your mailbox automatically into English? So this is a very smart way of how we embed machine translation into our day-to-day applications so that it's easy and convenient for the user, as opposed to me all the time seeing this text in French and having to copy and paste it onto a Bing Translate or anything. It very smartly knows that more than 90% of the emails that comes into JL's mailbox is in English, hence maybe she prefers to read in English. So this is very effective ways of enhancing our lives and convenience. The next thing is, if you think of the current landscape of the corpus of data that we have. So most of our content is either in one language or the other. So very rarely do you have parallel corpuses of data. So identical content in English, French, Hindi, or whatever. So bulk of the content that gets generated is in one language or the other. That's about 95%. I think slide's a little dated. And then if you look at the top 10 languages, which is here is English, Chinese, Japanese, French, German, Spanish, Portuguese, Russian, Italian, Korean. they account for about 81% of the content that's getting generated. Now, why do we need machine translation? I've showed you one use case, which is I want to learn a new language, or I'm trying to read an email that comes into my mailbox, but there are obviously many more applications. So machine translation can be used to augment human translation productivity. So think of scenarios like Facebook newsfeed or Twitter newsfeed. So these are scenarios where very often the content changes or is created too quickly and needs translation done at a very rapid clip. So this is where it's not actually practical to have a human translator for the scenario, because information is getting generated so quickly and it's impossible for a human to do this round the clock for 24 hours a day, 7 days a week. This is where you want an automated machine translation system. The other scenario is there are scenarios where for some low resource languages, often finding and hiring translators is difficult and expensive. So this is where if we can leverage learning from one language into these learnings in these low resource languages, it might actually help us. So this is why machine translation is actually needed in our day-to-day lives. Now let's actually think of, so we know what is NLP, we know what is machine translation. Now let's think of how this entire domain's kind of evolved to the state at which it is right now. So essentially, if you were to segment this, you can segment it into 4 different groups. One is the rule-based machine translation. So I'm starting all the way from the left where you see the green box highlighted. So that is the rule-based machine translation. So essentially, you know, just like how we would think of machine translation, there are a bunch of rules created by expert linguists who know, let's say, English and French. They know how to translate text from English to French and French to English. They know they're experts in these 2 languages. They know the rules, they create the rules, and we follow the rules when we do it. But this is not very scalable. This is not very scalable, as well as, you know, to kind of put it into a production scenario like a news feed or anything. It's not sustainable. Hence, you know, rule-based machine translation evolved into example-based, where you kind of have a few examples and you're trying to see if the new data follows the sample examples. Then in the 1990s, for about 15 years, there was a lot of work done in statistical machine translation. So that is short form as SMT, is where we use statistical models that learn to translate text from source language to target language, provided you have a large corpus of data. So, you know, a lot of data gets collected, you give it to the model, so you kind of build word-based, syntax-based, and phrase-based models. Now, over the last 5 years, there's been a lot of work done in neural machine translation. So that's where you hear of recurrent neural networks, RNN, LSTM, long short-term memory networks, etc. So neural machine translation, or NMT, is the use of neural network models to learn a statistical model for machine translation. So over the next few slides, we'll actually get into what is a rule-based, statistical, and neural. And towards the end of the talk, we'll actually focus on the neural machine translation, which is what we use in Bing Translate, etc. Okay, so like I said in the previous slide, statistical machine translation, or SMT, is either word, phrase, syntax-based translation, and it kind of learns word alignments between the source and target text. So if you see the examples on the right, you note that many a times the order of the words get flipped, or maybe one word in one language maps to many words in the target language, etc. So there are many combinations when it comes to languages. So essentially we have a source language model, we have a translation model, and a decoder, and it does all this for us. So now this was not very efficient, so that's when everyone did a lot of research, and neural machine translation seems to have the highest effectiveness in translation. So here the entire goal is to model the entire machine translation process via a really big artificial neural network. So you essentially have an end-to-end encoder decoder structure We will get into this in more detail, and then you'll understand what an encoder is, a decoder is. This is the little theoretical part that I said that we'll look at in the language model section. Okay. So now the next one that we'll actually look at is some of the applications of machine translation. So I think we all have APIs where here you can kind of type in text, like in bing.com/translator, and it'll actually even detect the language. So in this case, I do not understand the script, so it automatically detects it as Tamil, and it says, well, this is actually hello in Tamil. So detecting a language is sometimes also a problem, because many a times we get a huge corpus of data, and if I don't understand the language, I don't even know what language documents I'm looking at. So detecting a language is the first step. Once you detect, maybe you want to translate it to multiple languages. So we have websites in many languages. We might have customers in different regions around the world, and you need the email sent in different languages. So in this case, if you look at it, English, I know well. If I want to greet somebody, I say hello. But you know, in one API call, I'm able to actually get the translation in French as salut, German as hello, and in Arabic as marhaba. So this in one go gives you translation in multiple languages, which is kind of helpful. Then you have the other case, which is transliteration. We did see a bit of this when we looked at the English to Hindi, where I don't know how to read the script in Hindi, and it gave the little text in English where you could read the Hindi using the script that I know. So this is essentially convert word and sentences from one script to another. Here is an example where in English you're trying to say, where is the closest train station? I do not know how to read simplified Chinese, so it kind of gives it in English-like script so that I know how to say it. And so if I'm going on a visit to China and I need to say something, I can use this transliteration option. Obviously, you have the bilingual dictionary where you can search for examples of human translated sentences using the input word and find alternate translations for the input word. Okay, so these are some of the applications of machine translation. And now let's get into the theoretical piece. So this is just some basics. It's no way that comprehensive, and I think there are links to academic papers throughout where you can kind of read if you're interested. Okay. So the underlying concept in most of these things is something called a language model. So the goal of a language model is to compute the join probability of a sequence of words. So assume there is a sequence of words where I say my name is Jaya. So that would be word 1 would be my, word 2 would be name, word 3 is, and word 4 is Jaya. So we are trying to predict the join probability of the sequence of words, probability of W1, W2, W3, so on. It depends on how long the sentence is. It could be as short as, you know, a couple of words or many words in a sentence, or you want to compute the conditional probability. So assuming word 4 is Jaya, what is the probability that word 1, 2, and 3 is my name is, you know? So it's a very simplified scenario, but that's what you're trying to visualize in here. So the goal of the model is to compute such a probability of a sequence of words or the conditional probability. So we've seen this applications of this, and I think when I kind of highlight the applications, it'll immediately click and say, oh, I've seen this in real life. So supposing I'm trying to do machine translation, the word big from one language to another. Big and high might be almost synonymous in some languages. So, you know, the language model will say that big mouth has a higher probability of occurring as a sequence of words as opposed to high mouth. We don't hear people say in English high mouth. That's a thing. Then speech recognition. So many a time, so supposing I were to speak into one of my personal assistant devices on my phone, Siri or Cortana or Alexa devices, I might say, I love reading, Alexa. And then, you know, sometimes it gets the word reading as 2 words. Maybe I've given a certain pause between the words and it takes it as read in, R-E-A-D-I-N-N, as opposed to a single word read in. R-E-A-D-I-N-G. So essentially, the language model will say the occurrence of the word I love reading as one word is higher than the other, where it's 4 separate words. Then spelling correction. So many times when we type messages, when we say type, we might just misspell it as T-Y-E-S-P. So essentially what language model will do is it'll help with the spelling correction. So it'll say that, the probability of T-Y-P-E-S is way higher in the corpus of data compared to T-Y-E-S-P. Now, if you look at the approach, it's essentially using chain rule. This is a little mathematical, but you don't have to worry too much, but I just say it for the audience who are interested. So essentially we're trying to do is probability of word 1, word 2, word 3, word 4 equals the probability of word 1 multiplied by probability of word 2 given word 1. So that's the conditional probability of the second word occurring given the first word times the probability of word 3 happening conditioned on word 1 and word 2. And finally, since this is just 4 words in a segment, is probability of word 4 given word 1, word 2, and word 3. Little technical, but I think it'll be helpful in the long run. Okay, so then another thing that you want to know about is sequence to sequence. So essentially, if you think of these language models, the input is a sequence of words, like I showed in the previous slide. Output is also a sequence of words. Okay, so an example would be translation, like I said. So here I'm interested in translating English to French. So maybe I want to say Mary has a little cat and I want to know how to say it in French. And I might say Mary a un petit chat. And then it kind of tells you how to do it as well as how to read it and even speak. The audio clip is available. Then speech recognition also, many a times, we speak and it gets converted into text. I think, for example, Microsoft PowerPoint has the transcribe feature where it really is helpful for people who have difficulty listening or people with disabilities. So there are a lot of applications of this. Now, sequence-to-sequence learning with neural networks actually started off at Google way back in 2014. I mean, just about 6 years ago, but it did pick up quite a bit of momentum. So deep neural networks work well with label training data. They cannot, however, be used to map sequences to sequences. So one of the biggest problems with language is when you translate from one language to another, we cannot guarantee that the number of words in the input and the target language is the same length. So like in the previous example, you see that I think here, yeah, it's 5. Mary has a little cat and French is the same, but there are many cases where it's not at the same length. So deep neural networks was only applied to problems whose input and targets can be sensibly encoded with vectors of fixed dimensionality. And this fixed dimensionality is not always the case for language translation. And then sequences pose a challenge for deep neural networks because deep neural networks require that input and output length is known ahead of time. So here's the paper on arXiv in case anyone's interested in reading about it. Okay, so that's where the encoder-decoder architecture kind of played a big role in helping simplify this whole process. So you have the input text that gets into an encoder, and then you kind of create this red block, which is the fixed dimensional vector representation, and then you decode it and you have your translated text. So essentially you want to think of the encoder. It could be an RNN, LSTM that reads an input sequence one time step at a time to obtain a large fixed dimensional vector representation as what you see in that red block in there. Then essentially the decoder, which would also be an RNN and LSTM, can extract the output sequence from the encoding, that is this context vector. So now what you see is the variable length input sequence gets converted into a fixed length context vector, and then that gets reconverted into translated text, which could be a variable length output sequence. So this gives that little flexibility which is needed in languages and language translation. Okay, so now these are some, so I think I think I've alluded to this over the past couple of slides, where the main thing about an encoder-decoder architecture is it can capture linguistic regularities and rules and phrases. It can improve translation performance, and it can learn continuous spaced representation of phrases that preserves both the semantic and syntactic structure of the phrase. Again, there are papers. There are links to our papers on arXiv if you're interested. Then after a certain point of using encoder and decoder, they kind of notice that, especially with texts that have very long sentences, many a times the encoder decoder by itself wasn't doing a good job. So then they came up with something called encoder decoder architecture with attention. So like I said, so the pure encoder decoder structure only utilizes the last output to create that context vector, and the hidden states are not used in the decoder. So essentially with this attention layer, it kind of extends this encoder decoder structure by allowing the model to kind of automatically soft search various parts of the source sentence and pick the relevant ones for predicting the target. So I have an animation in the next slide which will kind of help you understand this slightly better. So here's how the attention mechanism actually works. So this is an English sentence where I'm trying to translate the sentence. I just want to have a sister. So now I'm trying to translate it into French, where you see that darkened blue line. So I maps to je, and then you see how some words like sister maps to saw. So essentially, and the other words in the corpus have much less weight to each of the words. So this is what the attention mechanism is doing. So it's kind of trying to figure out, how do I weight all these different things? Yes. And then they also do a little bit of alignment learning for models with encoder decoder. So this is something, again, so you see the English word, which is this will change my future with my family, the man said, and then you kind of see which different words actually map to the equivalent French translation. Okay, so that was a little bit of theory. If you're interested, you can go back and read the papers. That's there in case you're interested. So now let's actually get into the technology piece as to how do I even use all this. Okay, so we've actually looked at the two stages. One is the encoding and the decoding. So one of the things is NMT, refers to neural machine translation. We'll look at the basics first. So the first stage is encoding, where we model each word based on its context within the full sentence, okay? And the second stage, which is the decoding phase, we translate this word within the context of the sentence. So actually, we'll get into this in slightly detail so you understand this slightly better. So model layer one. So each word is modeled in the context of a full sentence. So this is an English word. I think it's the blue house something. So essentially at this level, what happens is during training, the neural network creates a 500 dimension model for each word in the given language pair. Again, so the language pair in here is English to French, where it looks at various aspects such as word type, noun, is it singular, plural, gender, formality of the word, etc. Then the next thing that it does is the neural network creates a 1000-dimensional model for each given word given the context. Now this gets repeated for every word in the sentence. So the sentence in here is the blue house is something. Okay. Then what happens is from model layers 2 to n, multiple layers allow for better contextualization. So you have layers 2, so on to n, and each of the network architectures does a different thing. And then you create this green, final input matrix. Then, like I said, with a simple attention, simple encoder decoder structure, sometimes it loses the context if the sentence is too long. So you have something which is the attention mechanism, just like how you saw in the previous animation, where it is able to soft search between the whole sentence to figure out what makes sense. And finally, you have the decoder layer. So essentially the decoder translates word for the context awareness for each language pair. So here the language pair is English to French, where the translation layer is a neural network that's learned word translations based on the 1,000-dimensional sentence context. So then essentially it knows that the word the maps to low, as well as the blue house. So it's aware of the context, and it knows that the blue house gets flipped as the house blue, maison bleu, in French. So it learns all these different nuances. So it's kind of remarkable how the neural machine translation learns all this with a lot of parallel corpus of data, as opposed to having a linguist come and define all the rules and nuances. Okay, so now obviously nothing is perfect. So there are obviously issues with simple encoder decoder structure, like I said. So vanilla sequence to sequence and long sentences with more than 30 words, they tend to have poor results due to that fixed dimensional representation. So that's when, like I said, we use the attention mechanism. So then the next question is, which part of the source sentence do we need to focus on for translation? How much attention needs to be paid to different parts of the source? And that's where we have the context vector with weighted average to see which part of this input sentence that we give more weight to. Okay, so now obviously when we wrap up this section, let's actually think of the advantages of using neural machine translation. So one of the things is it's end-to-end training. So all the parameters are simultaneously optimized to minimize loss function of the network's output. Then you have the distributed representations for better sharing of word phrase similarities. Then you have better exploitation of context. Neural machine translation can be used for bigger context to translate more accurately. And obviously it's shown to actually generate more fluent text generation. So there's deep learning text generation, which is of much better quality, and sometimes it's as good as humans in some cases. Okay, so now let's get into some of the use cases. So we're done with all the theory and all that, and let's get into the exciting part where how do I use this? So Microsoft does have something called a speech translation system. So essentially you have the client app that you talk on your phone. It invokes a web API endpoint, and it actually gives you the translated text or the speech. So we have, it's obviously optimized for conversations, it's customizable, and you can send the voice, receive the translated text script, as well as text to speech translation. How does this actually work in the backend? So this is there also on the website where the user actually speaks, the speech gets into something called ASR, or automatic speech recognition. So many times when we speak, we're not always grammatically right. We might repeat a word. So here's a sentence where I say, can you hear me? Because I'm not sure that the Alexa or the Siri application can really hear me. So I say, can you hear me? So now, as you see, I said the word can 2 times, and that's not right. So the true text essentially looks at this and says, well, there's a repeat of the first and the second word, so let's get rid of that. And then it kind of looks at the word here and it says, well, HERE is not the right here in this context. It should be HEAR. So it corrects that. And once it does that, the next thing is it capitalizes. And this is like a question. So put in a question mark as well. So it's kind of corrected it. And once that's done, it actually gets into the entire translation. So here's a case where I'm trying to translate the text from English to Chinese, I think, and then it actually gives the text to speech and how is it spoken in the language. Now, throughout this process, it is helpful to sometimes get partial transcripts, final transcripts, and even partial and final translations. Maybe you want it for some follow-up work. Many a times the system might get something wrong and you might want to look at it, look at the language pair translations, and then give the edited, proofread, updated transcripts back into the training model so it improves its performance for later. Okay, so throughout the process, you also have the option to customize things. You can custom your speech models, acoustic, the language models. You can do a custom translator, you can do a custom voice. So maybe you don't want the Alexa voice, you want a different voice for your IVR systems. All that is possible. Okay, so now the next thing is, like I said, is customization. It's kind of helpful to sometimes customize this whole thing. So we do offer something called custom translator, which is allows you to do neural machine translation customization. So general models that we have has very, it does not always have industry specific terminology. So general models are limited in that way. So if you think of the healthcare domain or things like law, finance, there are some terms that get used that do not get used in our day-to-day lives. We don't always use those words. So that's where you might actually want to build an industry-specific custom translator. Then obviously training neural machine translation models from scratch is expensive. It's complex, and then it needs GPU-powered cloud. Some of these models take days to actually train, and it actually needs a lot of data. And many times you need a lot of expertise. You need domain experts in NLP, language, acoustics to actually do this for you. So for many companies, it's really not worth that investment. That's where you'd rather go to either Microsoft and say, well, do you have a custom translator option where I can just feed in some data from the healthcare domain and it'll just help me do it. So the advantages of using our custom translator is you start with Microsoft pre-trained models, then you adapt them with your customer data, and it can be used with as little as 2,000 pairs of sentences in the 2 languages. It's easy, cost effective, fast, and can be done in the cloud. So obviously, let's look at the benefits of customization. So you actually measure performance of these models using something called Blue scores. Blue scores refers to bilingual evaluation under study. So if you look at this one, this is a general model. Let's say the Blue score is between 20 to 30. A human being is obviously the best, where it's about 50 to 75, let's say. And then the customized industry specific. So supposing I use some data from healthcare to translate text from English to French or something. Obviously, compared to a general model, the industry specific model has a bump in the Blue scores, and it's between 30 and 45. Obviously not as good as a human being, but not as bad as a generic model. So there's obviously a trade-off between everything. Human is expensive, these general models end up being cheaper. Okay, so here's an example where you essentially are trying to use a custom translator in a general category. So what you do is it's just a 4-step process. The first thing is you upload the parallel corpus of data. So here you're trying to translate French to English. So you have parallel data sets in TXT or whatever format that they support. You upload it. Then the next thing that you do is you train the model in the cloud. It's just a 1-click. Then you create the custom model. Then you can test it with some data that you held for testing purposes. That's obviously not used in training. Then many a times you kind of see that your custom model is slightly better than the general model. So in this case, it's saying that the Blue score increased by 4, which is kind of better than the general model. And then you essentially can deploy this as an endpoint with just 1 click. And then you notice that it essentially, so there's a general model, the specialized model, and you see that the translation is slightly better. Not always the best, but this ends up being better. So now the next thing is I'll actually, take you through some of the useful links, and then I should be open for questions. So here you see that I think the first set of links is for some of the blogs and some YouTube. I think there was a Stanford web series and some of the blogs that we have. Then the papers are the ones that gets into the technical sections. Then if you're interested in any of our product information like translation Then we have, I think, Translator Live, some support forums. And then here is, yeah, I think there's also something called Office Lens. I don't know if some people have used it. Microsoft Translator has an app. You can download it and use it. And yeah, so that's pretty much what I had. So I'm actually open for questions. And yeah, I think I have enough time for questions. So I run over to you if there are any questions for me.
Hi, Jaya. None yet, but I've just posted an ask for any other questions. So if anyone has any questions about any of the slides that Jaya has asked, please send them over. Hamza just asked, can you post the links in the chat? So is there a link in particular that you would want in the chat, or would you like?
Is it all the links? I can just copy all the links. Is that what you want? This one?
Sure. Hamza, if you could elaborate which link you would like, please let me know. Any other questions? If it's all the links, then yeah, Jay, I can post those as well.
Yeah, I'll just post the links in here in case anyone's. Did it post? Yeah, there we go. Yep. I think that covers. Yeah, I think these are essentially the links even in the slides. Yep. I think I put them all together.
Yeah, perfect. So Hamza just asked for all the links. Here, let me just copy paste all of these as well. And I'll see if we can share all the slides. Like, Jaya, do you feel comfortable sharing the slide?
Yeah, I can actually convert it to PDF and send it. It's much smaller. Yep.
Perfect. So we'll share those as well. I'll attach it to the YouTube recording and the meetup group that you came from. So yep, that's all the links. Any other questions from Jaya before we wrap up? I'll just give everyone a minute or two. Or if you'd like to go back to any particular slide from the presentation. Oh, I think we got one. So yeah, Hamza has another question. Can we use the model that we train to translate English to Hindi to translate Hindi to English?
Yeah. So actually, what is that? You'll essentially what you do is like the step that I showed here, where you have English to Hindi, no, French to English. So if you have English to Hindi and you can use it. Yeah. And I think if you do English to Hindi, if you just flip the order, I think the other one should work. Mm-hmm.
Perfect. Well, I don't see any other questions yet. So if everyone doesn't have any, we'll go ahead and wrap up now. There will be a survey link that will be available in the meetup group. We'd love to hear your feedback on the presentation, and if you have any feedback for Jaya or us, or if you had any questions about the audio. Fernando says thank you very much. So thank you for joining us, Jaya.
Thank you.
Thank you so much. So I'll have the recording up. I'll share the links with everybody. And thank you so much for taking the time out. Thanks, Jaya.
Thank you very much.